Okay, welcome to Lesson 3 of Module 6. This lesson is representations of a line. And in this lesson, we are going to be graphing lines specified by linear functions. And we're going to see how, again, this is kind of practice for you. So it should feel pretty familiar with some new twists. But we'll do it when we're either given the equation or given maybe the initial value and the rate of change for a situation, or even just given 2 points, and from those 2 points we'll determine the function. So let's look at an example and we'll work through this first example together. So rate of change and initial value given in the context of the problem. Okay, so here we're going to be given those 2 things. So a truck rental company charges a $150 rental fee in addition to a charge of 50 cents per mile driven. In this problem, you will graph the linear function relating the total cost of the rental in dollars, and we're going to call that C, to the number of miles driven, M, on the axes below. Okay, so notice right off the bat, we've got, instead of X and Y, we've got C and M. And so we'll have to keep that in mind, that cost is a function of miles driven. Okay, so we'll be graphing it here on this axis. So I'll be coming back and forth between these 2 pages. So if the truck is driven 0 miles, what will be the cost to the customer, and how will this be shown on the graph? Okay, so let's think about that for a while. And if the truck is driven 0 miles, we could think of that as our initial value, right? Because that's the initial value before the truck is driven at all. There's still going to be a charge. So let's look back at the problem itself to find the initial value. So the truck rental company charges a $150 rental fee in addition to the 50 cents per mile. So if the truck is driven 0 miles, the cost will still be $150. The $150 rental fee will be charged even if they don't drive the truck. Okay, and how will this be shown on the graph? Well, it will be the point where the first coordinate, which is the horizontal or the M variable, is 0, and the cost variable will be shown on the vertical axis for at $150. So let's go back and look at our graph, and we'll go ahead and plot that point now. So how will that be shown on the graph? So let me get my dot. One thing you need to notice here is that we've got dollars on the y-axis, and we have miles on the x-axis. So when miles driven is 0, the cost, which is what we're putting here, is 150. So that's going to be a point right about there. Get that on there. Right at 0, 150. Okay, so let's go back and do part B. What is the rate of change that relates cost to the number of miles driven? And explain what it means within the context of the problem. Okay, so the rate of change is we have this 50 cents per mile. So we could say that our rate of change equals 0.5. We could also say something like the cost will increase 50 cents every mile. Every mile driven, or every mile. Okay? So that's our rate of change in this. So part C, on the axes given, sketch the graph of the linear function that relates C to M. So we have 1 point already, so we're going to need a couple other points. And so let's look back at our graph to see which ones we might want to do. Okay, so the point we have is the initial value, just the rental fee for 0 miles. So we could pick a value here in the middle, like around 500 or 600, and then maybe we would pick 1,000 as well, and calculate what would the total cost be, and then we can connect those and draw the line. So let's come back over to this page here. So let's let, excuse me. So we'll let M equal 600, and then the total cost, C, is going to be that rental fee of $150 plus the cost for the miles. So for 600 miles, we're going to pay $300 because it's 50 cents every mile. So we've got a point where M equals 600, then the total cost is $450. So let's look at the next one. So if we do M equals 1,000, then the total cost is the rental fee plus $500 for the miles, which would be $650. Okay, so let's go back to our graph and put those on the graph that we have there. So we've got the 1 point already. So for, what did we have? For 600 miles, it was $450. And so that would be, right? Oh, wrong tool. 600 miles would be $450. And for 1,000 miles, that would be $650. And then we would hopefully find that, whoops, that's not what I want to do. Hopefully find that those would lie in a line. I'll get it. Here we go. Okay. Right about there. Okay, so they did. All three of those points were in a line, so we must have done something right there. Okay, so now we can write the equation of the linear function that models the relationship between number of miles driven and the total rental cost. So, and remember we're using C and M, not X and Y. So let's talk through this. So the total cost is C, and we'll just do it how we wrote it. The total cost is, and let's write it, we'll do the cost for miles first this time. So the cost for miles is going to be 1/2 of the total miles driven, M, 0.5 M, okay, 50 cents for every mile, plus our initial value of $150. Okay, so there's our linear function relating the miles driven to the cost. So cost is a function of miles driven. Okay, you can work on exercises 1 through 5 on your own and then just come back and check answers together. Very similar to what we've been doing, and then I'll ask a couple more questions of you regarding this example, and then you can go on to the exercises 6 through 10. Okay, so this this first one, Jen bought a used car for $18,000. She has been told that the value of the car is likely to decrease by $2,500 for each year that she owns the car. So that is very similar to the situation that we had in lesson 2 with in the aging cars. So you're going to work through this. It's a slightly different example. I want you to notice the scales on the graph, okay? Again, notice number of years on the horizontal axis is the variable t is going to stand for that. And value of the car in dollars is on the, did I say vertical? Is on the vertical axis. And it has a very different scale, 5,000, 10,000, and so on. So you're really going to have to use the change in the horizontal axis and compare it to the change in the value of the car carefully. You can't just, count off squares. So just be aware of that. Okay, so go ahead and work on this, and then come back and we'll check answers together. Okay, so exercise 1 says, what is the value of the car when t equals 0? Show this point on the graph. And so the value of the car would be $18,000. And we could think of that as the initial value, right? Because it's before anything happens. That's the value. So I'm going to plot 18,000. So it looks like each of these is standing for 1,000. 16, 17, 18. Right there. So there's the $18,000 at the brand new car. Or no, actually it's a used car, but it was its initial value is $18,000. Okay, so there's our first point. And what is the rate of change that relates V to T? So the rate of change, the value of the car is going to be decreasing, right? So our rate of change is going to be negative 2,500, because that's the yearly decrease in the value of the car. And the negative is important, right? Because that's going to show a decrease in the car's value. Okay, and it... all right, so the value of the car. Find the value of the car when t equals 1. Well, when t equals 1, it will be 18,000 minus 1 times 2,500, because it's just 1 year. And so that will be 15,500. After 2 years, we're going to do 18,000 minus 2 times 2,500, which is 5,000. And that's going to be 13,000 for the car. And then after 7 years, we would have 18,000 minus 7 times 2,500, which would be 1,400 plus 3,500, which would be 17,500, which leaves the value of the car at $500 after 7 years. Okay, so we're going to plot these points for the values that we found in exercise 3 and draw the line. So we need to go back to the graph to do that. So after 1 year, we found that the car was worth 15,500, so just not quite 16,000. After 2 years, we have 13,000, so there's 10, 11, 12, 13. And after 7 years, the car is worth $500, right there. Just barely above the line. Might go a little higher. My dots are kind of big. Okay, and so we can connect the dots here. and draw a line. Okay. And okay, so let's talk about this. So first let's go write the function. We'll finish this off and then we'll come back to this graph because there's some interesting things to discuss with this function. So we could write the linear function. So this is the one that we could write like this, because let's think about how we did it. We've got v for value of the car is equal to the initial value of the car, which was 18,000. And I'm thinking about how we did the calculation here. And then we're going to subtract off $2,500 for every year. And t is the number of years that we've had the car. So our function is 18,000 minus 2,500 t. And notice that you could also write it in slope-intercept form, and it would look like this. We could have the negative 2,500 t plus the 18,000 by turning this around. Okay? But the negative sign goes with the variable portion of this with the years. But these are equivalent equations right here. So let's go back and look at that graph, though, and think about how realistic that is. So she has been told that the value of the car is likely to decrease by $2,500 for each year that she owns the car. So in year 7, the car is down to $500. Now, you haven't done a lot of shopping for cars and buying cars, but that seems like a really good deal for a car. So maybe this model doesn't work for all values of t. Certainly, what happens with our model after year 7? What's going to happen to the value of the car right here? What is this? The line goes below the x-axis, so what does that mean? That means the value of the car is actually negative. These are negative numbers down here. So that would be like she has to pay somebody to take the car. Well, that could be possible if she had to pay somebody to haul it away if it didn't work. But it's probably, if a car is $500, it's likely got something wrong with it or has been in a wreck or something like that. So I'm going to say that at a certain point somewhere in here, either the car doesn't decrease quite as much as $2,500 per year. Maybe for the first few years it does, and then maybe it levels off a little bit at a certain value down here around, a couple $1,000 or something. It's difficult to find a car for less than that. So these linear models, sometimes they only work for certain values of the variable, and that can be specified, and this might be one of those cases. Okay. All right, so the next set of exercises has to do with selling books. So we're going to have price and copies sold per day. So this is kind of an interesting one. It's a little different than other examples we've seen. An online bookseller has a new book in print. The company estimates that if the book is priced at $15, then 800 copies of the book will be sold per day. And if the book is priced at $20, then 550 copies of the book will be sold per day. So, so what are they saying then about this example? So I want you to look at this example and the exercises that follow, and then come back and we'll work on it together. Okay, so one thing that I hope you noticed about this graph has to do with where it starts. So a lot of times when drawing a graph, if there's nothing in the lower values, then you can do this thing where you don't use the origin. So this graph is actually starting at $15 for the lowest price of a book. And for copies sold per day, we're not going below 50, so we're not starting right at right at 0 for these. Well, actually, the vertical axis looks like the zero works on the scale. But for the price, it doesn't, okay? And that's okay when you're making a graph as long as the rest of it is evenly spaced, okay? You can't just have some kind of a jump right here in the middle. So once you start numbering, you have to be consistent, and they have done that. So, and you can think about the reason they may have started this graph at 15 is that's their minimum price for a book or something to that effect. So the rest of the graph would be irrelevant. So that would be one reason they might have done that. Okay, so let's look at this. So can we identify the ordered pairs given in the problem? Because we haven't really been told anything about rate of change. We're maybe going to have to figure that out from the example. So the ordered pairs that were given are ordered pairs of price and copies, right? So we said if they sold the book at $15, then they would sell 800 copies. And if the book was priced at $20, they would sell 550 copies. Okay, so we can plot both of those on our graph right away. So 15 goes with 800, and 20 books we would sell fewer. We would only sell 550, is that right? Yeah. So we'd sell 550 if we priced it at 20. Okay. Okay, so let's go, have to be switching back and forth here. Assume that the relationship between the number of books sold and the price is linear. So we're going to assume that it's a linear model here. The graph will be a straight line, so we'll go ahead and draw that graph on here. Starting at that point and ending right there. So that would be our linear model. Okay, and what is the rate of change relating number of copies sold to the price? Okay, so let's think about our rate of change. Let me get a different color here. We're going to, on the vertical axis, we go from 800 down to 500. 500 or 550? 550 copies. So from 800 down to 5. This isn't that easy, you know. Down to 550. Okay, so somewhere in there. And then the increase in price is from here to here. So that's kind of our slope triangle is roughly there. Okay, so the change in so we had a $5 increase in price, and we had a what was the decrease? About $250 decrease in number of copies sold. So this is negative 250 here, and this is plus 5. Okay, so let's see what that rate of change is. So we had rate of change. So we have negative, negative 250. So 250 fewer copies sold with a $5 increase in the book. So this rate of change, 250 divided by 5 is 50, and it's a negative 50. So, okay, so that's all we need to do for that. So let's keep going. Based on the graph, if the company prices the book at $18, how many copies can they expect to sell per day? So let's go back to the graph and look at that. So use my arrow here. So if they price the book at 18, I'm going to follow my graph up here. and then come straight over there. And it looks like I can expect to sell 650 books. So we could draw that line on our graph too. So what you're doing here is 18. So if the price is $18, we're going to sell 650 books. 650 copies right here. Based on the graph, approximately what price should the company charge in order to sell 700 copies of the book? Okay, so this is kind of an opposite question, right? So if I'm going to sell 700 copies, then I'm going to come right over here where copies sold is 700, follow it over, and then see that it looks like I should charge $17. And if I want to do that here and come right down, $17 looks like what I would want to charge. $17. Okay, so now it didn't ask you this in exercise 8, but I would like to say, could you interpret this rate of change of negative 50? What does the rate of change of negative 50 mean? And put in words. And this is, for those of you who were in class on Monday, we did this with blood pressure and heart rate. And we tried to put into words what the rate of change meant in the context of the problem. So think about this, but what you want to say is something to this effect. Think about it first. You can pause me if you want. I would love to have you here and get your responses, but I'm going to have to do it virtually here. So we could say that the number of copies sold decreases by 50 for every $1 increase in price. Okay? The number of copies sold decreases by 50 for every $1 increase in price. And I could say it backwards too. I said for every $1 increase in price, the number of copies of books sold will decrease by 50. So do you think this situation seems reasonable? Why would the number of copies sold decrease as the price increases? I think we can probably all relate to this. It does seem reasonable because the more expensive a book is, the fewer people can afford it. People aren't going to be as motivated to pay $20 for a book as to pay $15. So it's an interesting situation. So this is a decreasing function because as the x values increase and on the horizontal axis, as this increases, the y value decreases, which makes the line slope down here. So as x increases, y is decreasing. As the price of the book increases, the number of copies sold decreases. Okay. So we're getting a lot of good practice with these. You guys are going to know these backwards and forwards. Now I want you to look at what they've done here. When the rate of change B and an initial value A are given in the context of a problem, the linear function that models the situation is given by the equation y equals A plus bx. Okay, so don't be thrown by the change to A and B. They're just constants, okay? A and B are just the slope, the rate of change, and the initial value. also known as the y-intercept. So the important thing is that the rate of change is the coefficient of the variable term, the x term, and the initial value is the constant term, meaning it doesn't have a variable attached to it. Okay, so the rate of change in the initial value can also be used to sketch the graph of the linear function that models the situation. So we can do that. Or if we're given two or more ordered pairs in the context of a problem that involves a linear relationship, the graph of the linear function is the line that passes through those points. And the linear function can be represented by the equation of that line. Now, we didn't do an equation on this line, but we certainly could have. But we will be doing more of that. So we'll go ahead and you can work on the problem set for lesson 3.